Hello, this is video 35. I'm going to finish up the examples with centripetal force. This time we're going to look at objects moving in horizontal loops. Let's look at this your turn. When a car turns a corner on a level road, which force provides the necessary centripetal acceleration? So it's asking which one is the centripetal force. And we've already seen this, so hopefully you know the answer. And it's just like the coin on the turntable, right? So if there were no force, the car would just keep going straight. It wouldn't be able to round the corner. You've probably tried to drive on ice and you can't make a turn, right? You just slip because your tires don't grip the road. The tires need that static friction, and the static friction prevents it from slipping. So instead of going straight off the road, that friction force points toward the center of the circle, provides the centripetal force, the centripetal acceleration, to allow the car to make that turn. So now that we know that, we can go ahead and do this example. What's the maximum speed with which a car can make a turn around a curve of radius 20 meters on a level unbanked road, so it's a flat road, without sliding? And we are given the coefficient of static friction. So whenever we have a centripetal force problem, the first step is draw the free body diagram. So the circle is horizontal this time. I'll just draw it just like it is. The object is right here. So there's a static friction force that's providing the centripetal force. Now you probably also know that, well, what about the normal force and the weight? Right? If you look at the car from the front here, then you know, or let's say from the back, you know that there's a normal force and a weight. In this case, the static friction would be going this way, right, toward the center of the circle. Well, we don't care about the normal force and the weight as far as centripetal forces are concerned. We only care about forces toward or away from the center of the circle. So, when we do a free body diagram, all we need is a static friction force, and then we can sum up our forces equal to mv squared over r. The static friction force is going to be positive because it's toward the center of the circle. And then we have to figure out, well, we're trying to go at maximum speed. That means that if we were to go any faster, we would slip. So when we're on the verge of slipping, that means we've reached our maximum static friction force. So we can substitute the static friction force for its maximum value, mu times n. And then we can make one more substitution. If we look at this free body diagram here of the back view of the car, and we look at the y direction going up and down, we are in equilibrium in the y direction, right? The car's not jumping up and down. So in the y direction, we can say the sum of the forces in the y equals 0, and that will give us the normal force minus the weight equals 0, and that will give us that the normal force equals the weight. So you probably already knew that without having to go through this, but it's good to go through the motion. So now we can substitute the normal force for the weight. Because remember, this is not always the case. You always have to solve for normal force to know what it is. It's not going to be equal to the weight by default. And now we see that the mass cancels out, which is why we were not given the mass of the car. And now we can solve for the maximum speed here. We can multiply by r and take the square root. So the maximum speed is going to equal mu times g times r, and then take the square root. So now we can plug in our values, and we're going to get, so take the square root of 1 times 9.8 times 20, and I got 14 meters per second. So that's the maximum speed that we can go, and any faster, and then we would slip. And just for your reference, this is approximately 31 miles per hour, so it's a reasonable value. So let's take a look at one more example here. This is your turn. A car turns a corner on a banked road. Which of the diagram could be the car's free body diagram? It's kind of weird. Why does it say could underlined like this? So the reason is because usually when you see a car on a banked curve, the problem is going to say there's no friction. And the point is that it's the normal force that is providing the centripetal force, keeping you from sliding up or down, and that you don't even need static friction force to be able to move in your circle. So if we're on the surface here, we know there's a normal force on the car, so we can eliminate choice D. And we know that there's a way, the weight always goes straight down, so we can eliminate choice C. So now we have three more choices. Well, A and B have some kind of horizontal force either to the left or to the right. But if we look at the car here, what could be providing a force to the left or the right? There's nothing there, right? The surface is at an angle, so there's no horizontal force. There's no wind or anything like that. So those are not good options. So that means by process of elimination that choice E is our best possible answer. So we know that this top force here is a normal force and the bottom force is the weight. So what is this force going down to the lower left here? Well, this is actually a static friction force. You can see it points down the incline. So it prevents the car from sliding up the incline. Now the reason it says could here is because the static friction could also point to the right, upward like this, in order to prevent the car from going down into this incline here. And this just depends on how fast the car is moving. So we don't really want to worry too much about the static friction force. What's really important about this problem is that if the problem says that there is no friction necessary in order for the car to make a circle here, then the normal force is what's going to provide that centripetal force. Because if we look at it, that normal force has a component to the left and a component upward. So that x component, which I'll call nx here, is the one that is pointing toward that center. See how the center of the circle is right here? That left component pointing to the left is providing the centripetal force. No friction necessary. So just to recap, when you have a car that's trying to make a turn, it's going to be that static friction force that's going to provide a centripetal force. If you're on a flat surface, if you're on an angled surface, then it's going to be that normal force that will provide the centripetal force. Even though this particular U-turn did make use of the friction force, it was just the best choice. But in the problems that we're going to see, there's not going to be any friction force when we're on a banked turn.